Hello everyone and welcome. So I figured we'd start today off with a nice little problem to start things off here. So you can see you have this sort of situation, DE is parallel to BC, and you're given a bunch of information here. You have this is 8, this is 2, and this is 12. We want to find the length of EC here. So we are given this sort of thing here. We can try to figure out what's going on. So I think it's a good idea for you to take a few minutes and try this problem out first, and then, come back to the video and take a look at what's happening. Okay. So, parallel sides. Parallel segments here are always good things because with parallel lines and other lines here come congruent angles. In particular, notice how ADE and ABC here, these here happen to be congruent corresponding angles here for the parallel lines, right? And of course we have, we can't forget angle A congruent to itself. And we also have the fact that angle AED and angle ACB are congruent here. So in fact we have 3 pairs of congruent angles. We really only need 2 pairs, but 3 pairs exist here. So it's pretty clear here that we have ADE being similar to triangle ABC here, right? We can show that that's the case here. ADE and ABC are similar triangles here. So that means now we know about similar triangles. Similar triangles are congruent corresponding angles, and they also have corresponding sides that are in proportion here. So we can write a proportion like this. We can say that AB over, in this case, AB to AD. So actually, let me write it out differently. I can write it as AD over AB here, like that. AD over AB should be equal to AE over AC here, right? And now we can just substitute the numbers in. So we know this is going to be 8 over, AB. Well, AB is the entire thing. 8 plus 2 is 10. And we have AE over AC, so that is 12 over AC here. So we don't know what EC is, so I'm going to call it X. So we can write this as 12 plus X here, right? So now we have a nice little proportion to solve here. So we end up with 8 times 12 plus X equals 120. So I think you find that 12 plus X equals 15 here. So you get X equals 3, right? And that's EC. Nice. So that's a nice, simple, little problem here. But wait, you may exclaim, there's another way to do this here. Shouldn't we be able to write this? So some of you may have also considered this here. 8 over 2 equals 12 over y, where y is equal to EC here. You get 8y equals 24, and therefore y equals 3, which is EC. Hey, that seems to work too. So notice that we have 2 different solutions for this. But here's the thing. Consider the following here. If you look at this proportion, what is this proportion really saying here? Well, let's see. Notice how here we had our segments written out. Here I want to do the same thing. So we have 8. So 8 is AD. I can write this as AD over DB equals AE over EC here. Now note that this first proportion here, this one we know was true because we know that corresponding sides of similar triangles are proportion. But here, the thing to note is that DB and EC unfortunately are not corresponding sides here. They really aren't, right? They just look like, in this case AD and AE are sides, but DB and EC aren't. So technically this thing should fail. This proportion shouldn't work because I'm comparing a side to a thing that's not a side. And yet we end up with y equals 3 at the end here. So, there's got to be something going on here. There are very few coincidences in mathematics here. Something happens like this, chances are there's a reason for it. So we're going to investigate this a little bit more here. Okay? So what's going on here, ladies and gentlemen? Well, let's see. The thing to note here is that, first off, the fact that this proportion exists is that, notice how AD and DB are pieces of this side AB. Similar, AE and EC are pieces of this side AC here. So we can actually give that piece of information terminology here. So we refer to this here, ladies and gentlemen, as the following. So we say that they are divided proportionally here. So 2 segments here, 2 segments here are divided proportionally if and only if the ratio of the lengths of the pieces of one segment is equal to the ratio of the lengths of the pieces of the other. In this case here, if we look back at the do now, or rather back at the problem that we started with here, we have that 4-to-1 ratio here. So notice how here 8 to 2, that's a 4-to-1 ratio. We have a 12 to 3, that's a 4-to-1 ratio here. So these are each 4-to-1 ratio, so therefore we can say that this divides the segments proportionally here. So notice that DE divides AB and AC proportionally here. So what seems to be the case here is now that we have this definition, excuse me, now that we have this definition here, it seems for us to say, hey, wait a minute. It seems like the fact that we had a parallel side of a triangle here, it's going to create proportional sides here. So it seems that we have something that looks like this here. If a segment is parallel to one side of a triangle, then it must divide the other 2 sides of the triangle proportionally. Okay, that seems fair, and I think that that's something that we can take a look at here. So we're going to try to figure out here how to prove this particular theorem here. So this theorem, we're not exactly sure if it's true or not, but I suspect that it is. So let's go ahead and write this one out, okay? So note that in this situation, the only piece of information we have is that DE is parallel to BC here, right? And we want to prove here, in this situation, we want to prove a proportionality business here. We need to prove in this situation here that the ratio is the same here. So I'm going to write it as BD over AD equals EC over AE. Now, granted, you could write it the other way around. You can write AD over DB equals AE over EC. It's still going to work at the end. It just simply means we have to do, take the reciprocal of both sides at the end here, and it will still work out very nicely. Well, all right. I mean, considering what we did here at the beginning, there's really only one thing to do here, right? We know we have this here, so we can use similar triangles. So it seems like we're going to have to go that way anyway. So at this point, let's give this a go here. We can actually write this out formally here. We mentioned that we have congruent corresponding angles here, right? So we can go ahead and mention that here. I'm just going to jot that down here. So we note that in this situation here, angle ADE. Now notice I'm not writing a formal proof here. I'm just simply jotting down the major ideas of one. And you can very easily turn this into a formal proof by simply converting this into the two-column form or converting this into a paragraph here. So we know ADE is congruent to ABC here. And we also know that angle A is congruent to itself. So I'm going to mark that up here. Right? So these are corresponding angles from parallel segments. Right? So notice that we have our corresponding angles from parallel segments. ADE and ABC are congruent. And this is our reflexive property here. Okay? So that seems to work out here. So therefore, we can use these two pieces of information here, right? And we can therefore say here that the two triangles, in this case ADE, is similar to triangle ABC here, and this is angle-angle, right? So angle-angle similarity works out very nicely here. Okay, now we need to start doing a couple things. Since we know that corresponding sides of similar triangles are in proportion, I can write a proportion here. So in fact, I'm going to write a proportion here, and in this situation here, we're going to look at the sides that correspond with one another. Notice in this case, AB and AD correspond. They're both, in this situation, in case you don't see this here, one thing you might also want to consider is, think of this as if it were congruent triangles here, right? Notice that our blue dots here, these are our blue congruent angles here, and the corresponding sides are going to be the ones that are opposite the congruent angles here. So in this case, since these are corresponding here, these two blue angles are congruent, the sides opposite them, in this case, AD and AB correspond. Similarly, AE and AC correspond as well. So that means I can write here. So now this is where we're going to start writing it out a little bit more. We can say here that in this situation here, AB over AD equals AC over AE here. These are corresponding sides of similar triangles are in proportion. Okay. Now, that's all fine and dandy, ladies and gentlemen. We're not exactly done yet, because if you look at our goal, the denominators in our goal match, but our numerators don't, and that doesn't make any sense here. We don't want AB, we just want BD. We don't want AC, we just want EC here. So we need to figure out how to introduce those new characters into the system. Well, let's see here. What relationship do we see between AD and between AB and DB? Well, I mean, if you look at it, DB is a part of AB, right? So in essence, if you think about AB here, I can kind of rewrite that. That's really two segments added up together into one. So I can use the partition postulate and substitute this in, and I can write here that I can call this AD plus DB here, right? I'll write this over AD. Similarly, notice that AC here is a combination of two segments. It's AE plus EC. So I can write it like that here. So I can say AE plus EC over, in this case, AE here, right? Interesting. I mean, all we did was just use the partition postulate and then substitute it. We're done. Now, I recognize these fractions here. So, you may recognize this from adding fractions in elementary school or early middle school here. This is basically what happens when you add fractions with the same denominator, the numerators get added together. So what if I could do that in reverse? Basically, I can now split this apart. So this here is a sum of two fractions. I can actually convert this into something a little bit easier to write. In this case here, this is two numerators over a single denominator, so I can split it apart. And I can write it as AD over AD plus DB over AD equals AE over AE plus EC over AE. So notice all I did is on each side is I basically, took this here and split the fraction into two fractions here. And you'll note that it works because you can go backwards here. Notice that there is this, there's this back and forth here. You can convert from this to this here. It's kind of like a solution at equilibrium here. You kind of have dissociation and reassociation of your constituent ions here. So it's the same idea like this. Now, wait a minute. Why do we do this? Well, consider this here. AD over AD. Well, that's easy. That's just something divided by itself. That's just 1. So I can write this as 1. And then I have dB over AD here. Well, AE over AE, that's also 1. And then we have EC over AE here, right? And then I can just subtract 1 from both sides. These go away. And the 1's cancel out. And when the 1's cancel out, what's left is dB over AD equals EC over AE. And lo and behold, wouldn't you know, that's exactly what we're trying to prove. So we can see here that this theorem here about triangle proportionality actually works out here. We use a little bit of similar triangles here and some finagling with proportions here. Now, note that this is also a new tool, right? You don't have to actually use this theorem here. If you just want to focus on using similar triangles and using what we've already been looking at, that's fine. There's nothing wrong with that. But now we have another tool that's available to us here that gives us an alternate method here, okay? It's always good to have alternate methods in your arsenal of ideas here for problem solving. Even if you don't necessarily intend on using them all the time, just having it available to you is often a good idea here. We can keep this in mind.